Hello and welcome to our talk. We are pleased to present our work GOEmbed, Gradient Origin Embeddings for Representation Agnostic 3D Feature Learning. This project has been supported by the EU-funded Prime ITN, Meta AI and UCL, encoding information from 2D views of an object and their camera poses into a 3D representation is a very important operation for various 3D tasks, such as MVS depth prediction, 3D reconstruction, 3D generation, etc. Most of the existing methods use variants of the cost-volume construction operation for feature voxel grids, whereas recent methods have also started encoding into triplanes. However, no encoding operations exist for representations such as hash tables and MLPs. And what about if a new 3D representation is proposed in the future? Thus, it is quite challenging to propose a mechanism which can be applicable to any 3D representation. Towards this end, we propose GOEmbed. GOEmbed can encode 2D views into any arbitrary 3D representation. These encodings or embeddings can be further utilized to train sparse-view 3D reconstruction networks. They can also be used in training diffusion with forward models to do 3D generation while training only on 2D images. We now present our proposed method. Here are the mathematical notations used to describe our proposed method. Let the function g of c, d represent a static 3D radiance field, where c represents the 3D coordinates and d represents the 3D direction. Thus, g is a 4-dimensional vector field on a 5-dimensional space, mapping the tuple of c, d to sigma and RGB values. Here sigma is the density and RGB represents the radiance. Since g is a parametric function, we represent the parameters or the weights of the radiance field by zeta. And lastly, we define r as the rendering functional, which renders 2D images out of the radiance field. Thus, what we are looking for is the encoding function e, where O context are the observed 2D views and phi context are their camera parameters. The proposed GOEmbed operation is as follows. Note that we demonstrate this operation with triplanes, but it is applicable to other representations as well. We start with a predefined and fixed origin over the features of the chosen representation denoted by zeta 0. In this case, it's just a triplane with all 0 features. Then we render the origin from the source poses to obtain the origin renders. Finally, we obtain the encodings by backpropagating the mean squared error computed between the origin renders and the source views to be encoded with respect to the origin zeta 0. These gradient features obtained for the triplanes are defined as the GOEmbedings denoted by the zeta enc. In order to maximize the information transfer from 2D to 3D, we minimize this GOEmbed loss function. Here O target are some target views different from the source views. We perform extensive experiments on the OmniObject 3D dataset. Firstly, we train the standalone GOEmbed in the Plenoptic-Encoding setup without using a trainable reconstruction network. GOEmbed outperforms the Dyno V2 baseline encoder in case of triplanes and gets comparable performance for the voxel grids. The Dyno V2 baseline is not possible for MLPs. Then secondly, we compare performance of our GOEmbedFusion model in the 3D generative setting. GOEmbedFusion outperforms various GAN and diffusion baselines in the forward as well as non-forward settings. Here we compare the generated samples by GOEmbedFusion against the DFM, DiffDF and our non-forward baseline. Finally, we evaluate our GOEmbed Recon model in the sparse-view 3D reconstruction setting. GOEmbed Recon outperforms the LRM baselines which were trained with 4 source views on the OmniObject 3D dataset. Here we show qualitative comparison between LRM and our sparse-view 3D reconstructions. Finally, we talk about the limitations and the conclusions of our work. In terms of limitations, firstly, the GOEmbed encodings are limited by the architecture of the denoiser network for 3D generation. For instance, we don't know which network architecture could operate on hash tables. Secondly, our 3D generated samples exhibit some checkerboard artifacts. We will find what causes them in the future work. In conclusion, we proposed GOEmbed for encoding 2D views into 3D while being agnostic to the underlying 3D representation. We showed application of GOEmbed to triplanes, voxel grids and MLPs while exploring other representations form scope for future work. And we also demonstrated GOEmbed in the 3D generation and 3D reconstruction tasks. Please feel free to check out our project page by scanning the QR code. We thank you for your attention.